My name is Brian Anthony. I'll chair the session. Really what that's going to mean for this session is I'll give you a case example of what we mean in this case about talking about modeling of matter. As you'll see, we're going to talk a lot about imaging of matter and how we use that to characterize or control the production of matter. In this session, we won't have a panel discussion at the end. So after each speaker, we should have time for 1 or 2 questions. So each person will have about 15 minutes or so. I'll try to keep mine under that. But be ready with your questions for each speaker after they go. Okay, so with that, our prior session was talking about novel computation, novel computers, the stuff on which we run algorithms. So it's nice to sort of connect to there. We heard a little bit as well about sort of the applications in medicine, so we'll make some connections to there. So imaging of matter. What we're going to talk about, though, is in many ways computational imaging, or modern imaging in some sense. So computational imaging is the intersection of collecting data and processing that data to make an image, right? Unlike what you think of maybe the way that your cell phone works, you don't actually see the raw data that comes off of your image sensor. You see a highly processed image, and often with their modern phones, they're taking multiple images to sort of create something that is sort of rich in experience and allows you to rapidly segment and have multiple focal planes. So, and I don't advocate this new selfie stick, but we benefit a lot from the types of computation that we can intersect with imaging. And image is a function of our data. So there are many forms of computational imaging, tomography, whether it be X-ray or ultrasound, imaging off of disperse and non-reflective surfaces, seeing around corners, for example, high dynamic range imaging, and many other examples. What I want to do is I'll start with ultrasound tomography. I'll use ultrasound as a motivating case example for how we think about this session being the intersection of imaging physics, imaging data for characterization and for process control where we're exploring or creating novel materials. So I'm going to start with the macro scale and give you an example of the space of computational imaging. What we're seeing in the middle is a low-cost ultrasound imaging tank where we have what's moving is a single transducer that is receiving the sound that is currently being generated by the stationary transducer, which is on the other white frame. The data that's being collected in this is the transducer that's stationary sends out a sound wave that you can see represented sort of in the bottom image if it's playing. Yeah, there it goes. And that sound wave goes into the medium that is in the water tank. In this case, it's a replica of a human limb. It bounces off of the interfaces and then goes out to be received by all of the virtual receivers that are around this tank. In this case, those virtual receivers are the moving platform. And the left and right images are the raw data that we collect. Now, those data can be put into the wave equation, and we can iteratively solve the wave equation to take those observations and say, well, what did the thing that the sound was propagating through need to be to explain our observations? So it's sort of a classical inverse problem where I'm going to collect all these data. I'll go through this iterative process of forming this image that's shown in the center to result in a final speed of sound image. Now, in doing that, though, it goes through this algorithm, this computation. The punchline of this algorithm, though, is what is happening is I'm comparing my observations, the data that I've collected. I'm iteratively running those data through a simulation, comparing those data to a simulation of the medium, the water tank with something in the center of the water tank, where I've simulated what the distributions of the density and the speed of sound are in that medium, propagate synthetic data, so simulated data through that, to generate a synthetic or a fake data set, and I compare that data set to the things that I've observed, and I sequentially over time converge until I figure out, well, what was that map? What was that image of what is in our domain? Now, I can do that. I can apply it to a lot of different processors, and because I'm iteratively applying a very complex, with lots and lots of data, full waveform, a physics model, it takes me a lot of time, 3 to 6 hours, just to collect one. The data set can be acquired in 10 minutes, but but it takes many hours to actually robustly solve that iterative problem. That's potentially a challenge, but I do get something nice and beneficial. By having all these data coming at different angles, I'm actually able to break what you might normally think of as the wavelength resolution of the wave that we're using. So the speed of sound in a medium has a certain wavelength. That should be the limit of the resolution that we're able to resolve, but since we have these data from different orientations around it, we're able to actually get something a little bit better than wavelength resolution. Now, if we had that data in real time, though, we could actually use it to control a process. So what type of process could that water tank potentially be used for? So we can sort of do characterization, and we can do online or sort of real-time characterization. So in this case, one of the motivating applications for this water tank phenomena is, can we collect data from an amputee sitting on a comfortable table with their leg, the residual limb in a water tank, have this ultrasound thing spin around them, and come up with an image that characterizes both the geometry of their limb in 3 dimensions, not just a slice, and also the tissue properties of the limb. If we have that type of data, and if we can do it in 10, 20, 30 minutes and not have to wait hours for this type of data, we could collect it, something like this. We could have then, instead of just a slice that is showing the geometry, the image, what you typically think of as the structure in your image, you could have both the structure and the material properties. And with those material properties then, I can then feed that data into an additive manufacturing process, or I can 3D print a socket that is the perfect geometry. It sort of matches conformally the outside geometry of the limb, but also has the correct material properties. So it's mechanically stiff where it needs to mesh, it's mechanically soft where it needs to mesh with the mechanical properties of the limb. Right? So I need to be able to acquire that data in real time, so I'm not having my patient sitting there in a long time with the prostheticist trying to form the cup that's matching me to my prosthetic. Okay, so if we're able to do something like that real time, then there's many applications. But how do we make it real time? How do we get around, how can we use sort of other computational approaches to get around the fact that fundamentally, if we really want to have that analysis, the mechanical properties be physically grounded, the structure be physically grounded, how do we use machine learning? How can we do some training to maybe think of a faster way to not solve the inverse problem, but a learned way to solve the inverse problem? And so when we're doing classical inversion, the way that we're going to do this is collect our data and iteratively solve a physics problem. But can we feed the inverse of that problem, so feed in the image the data that we're acquiring and automatically train a network to kick out the image? That's what machine learning could provide for us. But to do that, we need lots and lots and lots of data. And human data is really hard to acquire. So there's no easy source of the massive quantity of data that we'd like to acquire to teach a network how to very rapidly solve our inverse problem. The raw data that we get in and automatically fast kick out the image. Even if it takes a long time to train the algorithm, we can imagine the inverse running that inverse problem being fast. So we don't have a lot of really good, easy data to acquire on humans that would be the training data that we would need for this. But we do have really good physics models of the physics of the imaging process, in this case of ultrasound. We can write down the first principles of the wave equation, dispersive or not, in 2 dimensions and 3 dimensions. We can create a speed of sound map of some domain. We can simulate a transducer, the mechanical properties of the transducer, and how sound propagates through that. So we can create some really robust synthetic data. We can simulate then, for our imaging scenario, or the water tank and a residual limb put into the center of the water tank, we can simulate for as many different sort of virtual physical things that we want to put into that domain. We can simulate and understand what those ultrasound signals would be. And then we can flip it around. Now we have a physics-based or a synthetic way of getting our training data, and the input to a network for which we want to learn the parameters of how we map input to output data. The input would be the raw data that we receive. See if my laser pointer works here. Oops. The raw data, that's not the laser pointer. the raw data that we receive going into a network to automatically kick out the sound speed map. Now, machine learning is great for fitting within the boundaries of the data that it has observed. Right? It's not going to work very well for things that it hasn't observed. So just as an aside, one of the nice things about this type of approach, if we can teach a network to take our raw data in and get a good estimate of what the actual domain looks like, what the speed of sound map looks like, then we could also use that as the starting guess to our conventional or classical physics-based inversion process, that the closer that we can get our initial guess, the initial condition of that iterative loop, we don't have to be constrained to just having observations that our network's been trained with, but we can sort of get close and then still allow the physics to sort of do the things that are maybe outside of our observational space. Okay, so this is what a network looks like. That has allowed us now to first confirm with our synthetic data that if on the left we have, these are data that weren't used in the training of this network, the speeds of sound maps randomly generated. We trained a network how to do this imaging, how to create those images directly from the raw data that we acquire, and you see some of the noisy images that are generated on the right. Now, we've been able to do this now to do real-time imaging of this speed of sound map. So the tomography example that I showed you previously, water tank, this data that's collected over 10 or 20 minutes still takes 3 hours to reconstruct, to form this speed of sound map. The image on your right was collected and analyzed in real time, 30 frames per second. And it was that image inversion is performed by a network that we've trained with synthetic data, but these are now being applied on real data. So here, just to show one of the areas of how we're using this, if you take muscle, if you activate muscle, meaning you're loading it or unloading it, the speed of sound in the muscle changes. So if you have the ability to image the speed of sound of the tissue in real time, you can actually visualize in real time how your muscles are being activated. And so here we do an experiment in the immersion lab over at MIT.nano, where we go through this squatting exercise, standing on your toes and squatting, while we're collecting real-time ultrasound data of a probe attached to the side of the leg. And we can see through this false coloring, the coloring being corresponding to the speeds of sound in the muscle, the thing that we would expect to happen in normal healthy muscle, which is when we go from a standing to a squatting motion, that the muscle activation is going to go from the gastroc to the soleus, and then when starting in a squatting position back up to active, it goes similarly from the soleus back up to the gastroc. Right? Now, that is true in the situation where we have healthy muscle. We see this transition, the red going from the bottom, the red going to the top. But it also allowed us in this very small clinical study, an N of two people, we found and accidentally discovered and sent this individual off to get to actually see a doctor where that was later confirmed that this individual had nerve damage. They did not realize they had nerve damage, but their brain had learned how to rewire how their muscles activated. And we observed something very unusual in their muscle activation process through observing speed of sound maps from a network that had been trained with synthetic data coming from a physics model. Okay, so what I want to do today, and so here, just sort of that same idea for ultrasound scanning, we're also moving from the macro to the micro, and it can be used for doing things like characterizing of defects and voids through a package where you can see both the package and the internal structures. You can see delaminations and structures and things that you wouldn't see in an X-ray. You can see because you're able to visualize some of the mechanical properties that aren't visible in X-ray. But what I want to do today is for this session, take this perspective of, well, where does computational imaging, so this intersection of imaging physics and imaging data, allow us to impact metrology? So if we're doing offline characterization or sort of online in real-time characterization. And we'll see when we conclude with Julie that one of the points that came up earlier today where, well, how is AI actually allowing us to physically interact with the world? We have some interesting ways to connect image acquisition with robotic manipulation of helping us to discover and experiment with materials. And so there is early work that is helping us to sort of connect physical interaction with the world based on automatic decisions that an AI or an algorithm is telling us. So we're going to hear today first from George Barbastathis, who will talk a little bit about optical physics and machine learning for inspection and control. Bill Freeman will talk a little bit about visualization of the tiniest little motions, and so looking at how we can apply those in other domains. And then Julie finally will a little bit on autonomous exploration of materials. Again, we're not going to take questions at the end. We'll take them at after each speaker, except for me. And with that, I will turn it over to my good friend, George, and we'll take it away. Okay.
Thank you, Brian. Okay, so my name is George Barbastathis, so I'll be talking about something very related, actually. So I'm very grateful to Brian for the setup, I guess. First of all, let me acknowledge all my former and current students, especially those in boldface. So I'll pick up from where Brian left it. Basically, our claim here is that using machine learning in something like computational imaging, maybe it's a good idea, right? So I'll try to make the case for why it is a good idea and show you a few examples of the work we did in our group. So I think you're all familiar with these S-curves. It basically tells you that even if you're willing to pay a lot of money, at some point performance saturates, usually because of some physical limitation. And the technological innovation is actually to push up the S-curve, so you can either pay the same money and get better performance, or actually pay less money for the same level of performance that before used to cost you a lot of money. So the way we figured out how to use, how to shift up the curve in computational imaging is, as Brian very well put it, by a combination of optical physics and data and AI. And I'll show you a few cases. So we started working on this about 8 years ago, in 2016. Interestingly, it came up through a disagreement I had with a student of mine, Justin Lee. We had sort of an argument, and we decided to do this kind of work. But so basically, I'm touting my own horn here. But before that, I really want to acknowledge at least one other colleague, that is Professor Unzer at EPFL, who he started doing this at about the same time as us. And he showed that it is possible to reduce the dose of X-ray radiation on a patient by using AI. That was Unzer's accomplishment as far as back as then. So that was very inspiring for us. And then, of course, we did a lot of work, and I'll tell you a little bit about it. One of these had to do, can I go back? Yeah, okay, here we go. Yeah, so one of those projects had to do actually with integrated circuit inspection. That was funded by an agency called IARPA, where I stands for intelligence, and there's not the intelligence as in AI, that's the intelligence in the CIA acronym, okay? So I have no idea why they wanted to inspect circuits, but they gave us a project to do it. It's a really difficult problem, circuit inspection, because of course circuit features are very, very small. They go down to maybe a few nanometers these days. And also it's a lot of them. This calculation actually, I computed about 10 to the 18 voxels that you need. Of course, voxel is a 3D generalization of a pixel. So this calculation is already conservative. I did this a few years ago, and already the number of degrees of freedom in this imaging system is higher. So it's vast, right? It's sort of astronomical level complexity. And this is actually what drew us, what attracted us to this project. We thought AI can help us do it. So we succeeded, but it actually took us a long time to figure out what exactly AI can do. And actually, it comes down to time savings. We were able to do an operation that without AI would take a rather long time. We were able to do it 100 times faster. And you can see one reconstruction here of one such circuit. And also I should acknowledge that most of this data were taken at, actually not most, all of this data were taken at Argonne National Laboratory with a synchrotron. A synchrotron is a kind of a X-ray quasi-laser, okay? It is a vast instrument. Its diameter is a couple of miles, if I'm not mistaken, maybe bigger. And they were taking the data, and I think I put maybe I'll tell you a little bit about how this works. It involves two operations. In one of them, you kind of zigzag a beam over the integrated circuit and collect data. This is called tachography. And then the second step is you rotate the specimen as you know, with respect to the incident beam, and you repeat. You zigzag and you rotate, and you zigzag and you rotate. The rotation is tomography. Brian showed the sound equivalent of it. This is, of course, X-rays. And the combination of those two is called tachotomography. Now, why you need both steps, it's a little bit technical. So if you want, I can tell you after the talk. And I'm not joking here. Actually, for a full integrated circuit that you might use as a CPU or a memory somewhere, it would take a full year. I'm really not joking. A full year, it would have to sit in front of the synchrotron and be scanned and all kinds of computations. It's a really moonshot kind of problem. So we were able to reduce that by a factor of 100, which makes it, I guess, worth a few days. We did a scaled-down version. Let me tell you a couple of other things first. So one thing, we broke kind of a record there. One of the ways to reduce the time it takes to do this imaging operation is obviously to reduce the exposure, kind of like Unzer had done. But here we do it not because the circuit minds the exposure, we do it because we want to do it faster, right? So we kind of overdid it. We went down to 1 photon per pixel. Now, if you don't remember how much energy is in a photon, let me tell you that the level of illumination here is 10 to the 18 times less than the light we have in this room. 10 to the 18. That's 10 with 18 zeros following, right? That's the level of illumination that we used. And we were able to, you know, to actually get good quality images, as you can see, in a series of papers. And then we did the tomography problem. First, we did it with a toy problem, with a glass, actually, not a real AC, glass. But on the glass, we patterned things that look like circuits. In fact, we copied a CAD file from a real circuit, and that's what I'm showing here. And of course, people were making fun of us. They were saying, this is ridiculous. Why do you do it? This is not solving a real problem. But actually, thanks to this experiment, we did manage to solve the real problem. That's how we did the actual integrated circuit. Basically, thanks to what we learned from the glass phantom, we were able to figure out how to reduce the number of exposures in tomography and still recover the same quality of the reconstruction on the integrated circuit. So we did a lot of this analysis, and basically this shows you what is the limit of image, so that of how few exposures you can do without sacrificing any image quality. That is the purpose of this analysis here. And this is basically what the factor of 100 came from. Okay, so I'll tell you one more example. This is now in the pharmaceutical industry. And it is not imaging sort of objects like integrated circuits, but imaging powders, which are used in manufacturing of pills. This turns out to be a very delicate process, and you want it to be delicate because when you take a drug, it better be precisely the dosage that is prescribed, right? That's very important, and the FDA has a lot of very stringent requirements for how these processes should operate. So what you see in this movie there is one of the stages of this process where they have to dry the powder, and they have to do it carefully so it does not agglomerate. If it agglomerates, basically the FDA requirement will not be met, and the company will lose a lot of money. So they have people who look into the reactor and try to discern visually if the process is agglomerating so they can take corrective action. So we didn't do that. What we did is actually we simply illuminated with a laser beam, and then we do not even bother to image the power. We take the backscatter from the particles, from the surface of the particles, and then we use a physical law. It turns out with optical physics you can calculate something called the autocorrelation of this scattered beam. And then you can see in real time, we can characterize the histogram of particle sizes. So this is, of course, a control experiment where we know exactly the particle sizes and we can verify that they're correct. And then we did, let me skip this one and come back to it. And then we did experiments with actual processes. So you can see here the initial histogram is the red one. Then the process begins to agglomerate. It shifts to the right, which is blue. And then we pour more solvent. It shifts back to the green near the center. And then finally, near the end, you get something called attrition. The particles, due to friction, they actually begin to crack. And that's why the histogram shifts to the left. But you only see 4 curves here. In fact, there is thousands of curves here that we obtain at not quite video rate, but about half the video rate. So it's actually pretty fast. And our colleagues are very excited because this will allow them to physically quantify now this very complicated drying and other processes in the pharmaceutical industry. This was funded by Takeda, by the way, which is a pharmaceutical company with offices and labs nearby in Cambridge. I want to go back and show this because this shows that our neural network has learned physics. It turns out, I do not have time to go into the details, but the formula we derived predicts that the information about particle sizes is in the rings that you see around this. This looks like a comet of some kind. It's not a comet, it's this autocorrelation function, and the information is in the rings that surround it. And then you see these flame-like shapes. These are actually the activation patterns of the neural network that we use to solve this problem. And you can see, depending, of course, on the physical object that we put to test the algorithm, you can see that the rings kind of change, the neural network activation change shape to accommodate the rings that it thinks corresponds to the particles. So we're very happy. In my opinion, actually, this is the highlight of this work. It shows that the neural network it has been sort of built in a way that is weaving with the physics that govern this problem. The last thing, since this is a nano center and Bill is coming after me to talk about visualizing minuscule motions, I thought I'll show you something that we haven't published yet, and that's all right. This now has to do with nanomechanical motion. It is also a synchrotron experiment with a different group. This is one at Brookhaven, and you can see the names here, my friends from Northwestern and Stony Brook. And we try to characterize motion of nanomechanical devices. These are used in a number of applications, including quantum computing and quantum, basically, quasi-microscopic behavior of quantum systems. Very interesting devices, but we don't do that. Horacio Espinosa at Northwestern does it. We just help him characterize the dynamics of these devices. And this one looks like an easy problem, but it isn't, because we want to do it very, very fast, and also the problem is very undersampled. So if you had plenty of light, then you would get the signals that you see on the left. But again, I'm not kidding you. What you do get is this very, very highly undersampled pattern that you see on the right. That's our signal. These blinking dots, that's the only thing we can rely on. Okay, how we can pull it off? That sounds really, really awful. But actually, once again, we know physics. And in this case, it's not just optical physics. It does come in. But also classical dynamics, because this nanomechanical oscillator is sort of shifting according to something that we call, well, the harmonic oscillator, or maybe not so harmonic, but we can correct for that. Then we can set up an optimization procedure that will actually approximate the motion of the mechanical oscillator, even though the measurement is terrible, right? And what you see here is a movie that shows the evolution of this approximation process as we acquire a few time frames. It doesn't take too many time frames. I forget how many, but I mean a few hundreds, right? But not exceedingly high. Anyway, so that's another thing that we sort of just started playing with. This is a MURI project funded by the Air Force Office of Scientific Research. And we're very excited because not only it allows us to characterize complex dynamics, but also, again, I'm going to steal some of what Brian was saying. It will also, in principle, allow us to control these processes, right? Both in the pharmaceutical case and in these nanodynamics. it is possible to use what we produce to use it for feedback control. We haven't done it yet, but it's in the works. Okay, I think I'm going to stop here. I'm going to put up all the movies and happy to take your questions. Thank you very much.
So just a question, George. How do you see, so there's the physics that you can generate synthetic data with and sort of use it to here, but there's been a lot of talk as well about how do you embed physics into the network? Maybe you could opine about that.
Yeah, I mean, that's exactly what we did in this, actually in both cases. This is one evidence, as I was arguing before. In the nanomechanical oscillator, basically the way this works, again, I'm going to borrow something that Brian said. What this is trying to do is it's trying to guess, given this horrible data, it is trying to guess what is the best match of an object that is likely to have produced these horrible jumping dots. The difference is that here it is not only considering a static object, but it is actually taking into account the sequence of the frames that come as the oscillator is moving, right? Sorry, I keep saying oscillator, I should say the cantilever, right? As the cantilever is moving, it is taken into account. So basically what you have here, Brian, is you have a set of differential equations which are built in the neural network. I don't know how else I can say it without showing equations here, and I don't want to spill equations into your nice afternoon. But yes, there is a way to write differential equations that you may remember with nightmares from your college days or whatever. There's a way to weave differential equations with the kernels that deep learning uses to operate. This is what we have done here. And it is actually some of our colleagues at MIT, Alan Edelman and Chris Rakaukas, who pioneered this kind of idea. What we've done here is basically similar to theirs, but we've added optical physics, right? We've basically added the observation model, if you wish, to solve this very difficult problem. So I think this is actually where the future is, because physical systems are very often involve complex processes, complex dynamics, mixing complicated movements, and not necessarily robotics. I mean, this nanomechanical actuator is just as complicated as a robot, actually, if you want to look at it in detail. And yeah, I think there's opportunities there to get quantitative models where previously we couldn't. So I think it's very exciting. Thank you.
Okay, so next up, Bill Freeman, and sort of seeing motions big and small, and hopefully at all scales.
Thank you, and thanks for the invitation to be here. So this is work that's we've done over many years and involving many people, but the primary contributors, in addition to me, are there on the bottom, Mickey Rubenstein, Neil Wadua, and Professor Freda Durand at MIT. So science progresses in many ways by having imaging techniques that let us see things that we can't see otherwise. Of course, telescopes and microscopes have let us understand the world in ways that we couldn't without them. And what we wanted to do is introduce an analogous thing. Instead of amplifying the size of an image, we want to amplify the motion of an image. And I want to show you examples of that. So here's an input video of a baby, and often parents of perfectly healthy newborn babies ask, is the baby breathing? And so now we can see whether or not the baby is breathing with this motion magnification technique. And it works not only for small people, but also for large structures. So here's a crane, and you know that thing's blowing in the wind, but you can't really see it. But if you motion magnify it, then you can see those motions. So how does it benefit us to look at these tiny motions and amplify them? Well, one thing is I have this sort of mantra that big catastrophic motions are often preceded by tiny, almost invisible motions. So if you can image these tiny motions ahead of time, that's going to be useful. And also, you can learn things about the structure of the deformations by seeing it that you might not be able to otherwise. Okay, these next slides are just to persuade you that this would be something that's easy to do. You can do it in real time on low-cost hardware. And just to tell you how we do it, there are a number of ways to do it, but here's one simple way. If you take the image and instead of representing it by pixels, represent it as sine and cosine phase little wavelets like are shown here. So you would take that phase plate at the top left and you'd represent it by the filter responses shown at the bottom. You'd have these sine and cosine phase wavelets at, I have a laser pointer here. How about, I don't know. Sorry? The bottom button. Yes, I think it says laser. Yeah, okay. You have these sine and cosine phase filters at all different orientations and all different scales. And so here's 4 different orientations, here's the different scales. And you measure sine and cosine response. A tiny motion just changes the phase, the relative phase of the sine filter and the cosine filter just by a tiny amount, but you can measure that and amplify it. And, using this architecture, you can then have a very simple real-time system that takes an input video and gives you a modified output video with the motions amplified. I should say, as an aside, you can also amplify colors in a kind of analogous way. Here's on the left is someone just staring at us, and on the right is a video with the small color changes amplified, again, showing the benefits of visualizing things in a video. So I gotta say, this was one of the most enjoyable research projects I've had because I get to kind of look around the world and ask, where might there be tiny motions that would look interesting if we amplify them? And so I just want to show you a number of examples. The rest of the talk is just a number of examples, okay? And what I'm hoping you'll do is think, how might I use this in my own work? And, feel free to get in touch with me. I'd love to expand our set of examples to new things, and, there could be a useful collaboration to come out of this. So it's useful in physics. So here is a high-speed video. It's a PVC pipe viewed end-on. It's a high-speed video. That little hammer comes down and hits it. That's the input video. Now, you know from your high school physics classes what really happens when you hit the thing. It kind of rings like a bell, and there are these normal modes that are excited. And we can see those just from that input video. If we filter temporally to amplify motions at a very narrow band of frequencies that correspond to these normal modes, and you can search for the normal modes and find them, then you can produce these output videos that came all from that input video on the far left. And you can see that the amplitudes of the normal modes and what their shapes are. And I'm told that if there's a fracture in the pipe, it changes the normal mode structure, and you could perhaps identify that. So again, asking physicist friends, where are there small things in the world that are useful? So the transition to turbulence involves small oscillations that become bigger oscillations. There's something called the Tolming-Schlichting wave, which is a streamwise instability in laminar flow. So here's some incense. You can visualize in a video. There it is. It's easier to see what's going on if you freeze a frame. So on the left is a frozen frame of the input video. On the right is a frozen frame of the motion magnified video. And there you can see this, again, streamwise instability, sinusoid that gets bigger and bigger and then finally goes unstable in the transition to turbulence. Okay, engineering. So this is the inverted pendulum problem. So this is from Russ Tedrake's lab. They had a control. It's the pole balancing problem, but made even harder because it's got 2 joints to it. And this poor little controller at the bottom has to move this thing around so it doesn't fall over. The evil graduate students, in the one on the right, they loosened the bolts, so it's not the system that the controller is expecting to see. And in the ordinary slow motion video, you really can't see much of a difference between these 2 conditions. But if you take those input videos that we just saw and motion magnify them, then you can see that the one on the right with the loosened bolts is kind of struggling to control this thing because it's not behaving the way it expects it to behave because it's a different system than it was trained on. Okay, here's one that's fun. This is the bridge in Portsmouth, New Hampshire, from New Hampshire to Maine. It's got this structure that comes down. It's like a drawbridge, but it's horizontal and parallel. And when it comes down, it gives the bridge a kind of a kick. So then we went up there and just ordinary speed video, we filmed the bridge after the thing came down and gave it a kick. Nothing to worry about, everything's fine. But if you motion magnify it and select the frequency of the torsional mode, you can actually visualize what's going on with the bridge after that thing comes down and gives it a little kick. And there's tiny motions on the bridge that I think you don't even feel if you're on the bridge. And again, maybe these small motions will be useful to catch instabilities before they become big instabilities. And then it's fun to look at people, too. So here's my daughter, and I asked her just to stay still. So the top left picture is the input video of a person just staying still. Then we motion magnified different temporal frequency components of that top left video. So the top right video is low frequencies amplified. And what can you identify there? Well, to me, it looks like the breathing is amplified, and we can now see the breathing. The bottom left is kind of mid-band frequencies, 1 to 2 hertz amplified, and there you see these little micro expressions, and then people often ask, can you tell what she's thinking from those? And we have no idea. I really don't know if those imperceptible facial changes have anything to do with what she's thinking, but you could look into that. And then the bottom right is high frequencies amplified, and you can kind of see the eye saccades a little bit, and you can also see that we're starting to amplify noise in the background cabinets just from the sensor. And the beauty of the web is you can post the code online and people use it. So there's a graphic design student in Yale made this composite of, on the left side is the input videos, on the right side are motion magnified videos. I thought that was a nice design. And here's another one. This is also a pole balancing problem. A ballet dancer stands on one foot. And you know that there's all sorts of control going on to keep her from falling over. But now we can actually see it amplified. So on the left is the input video. She's perfectly motionless, it seems. And on the right, we can see all the control that she's having to do to keep from falling over. Here's one again that was contributed by the public. Someone posted this using our software. You can visualize motions of a baby in utero. The eye moves, so here's, again, left is input, right is output, and you can see these microsaccades. And it looks like a bowl of jelly underwater, which I think is probably close to what it really is. Jello underwater. And this one's fun. This is Mickey Rubenstein, one of the primary graduate students who did this work. Here, it's high speed. So the video we amplify can be ordinary speed or it can be high speed. Here it's high speed video, and he's going to sing for us. Okay, and then we record the sound and we record the frequency response from the audio. You can see that at the far right. So let's grab the fundamental frequency there, and motion amplify only oscillations in the input video which are at that temporal frequency. And again, this is straightforward to do. You just filter each of those coefficient pairs, narrowband filter for that frequency, and reveal what's going on in the throat. So that's on the right. Now you can see the vibrations from the outside of the vocal cords as he makes that sound. You can go and grab the first harmonic. So this is twice as fast, and you can see the little nonlinearities in the mechanical system. They're oscillating at twice the fundamental frequency. As a control, we amplified a non-harmonically related frequency, and you don't see anything special, which is good. Okay, and then, so finally, this one relates to nano. But all of these, so I guess the point is, you can do this with telescope data, you can do it with photographic data, you can do it with microscope data. All you need is to input a video. And it can be an ordinary frame rate video, it can be a high-speed frame rate video. And maybe there are useful things going on in your microscope images that you could usefully amplify the motions of and see something that you see some structure there that you weren't able to see before. So here's an example of that. This is from Denny Freeman's lab, no relation to me, but we work together. And he is interested in acoustic waves across a particular membrane in the inner ear. And so there it is. You know, there's the top is the input video. And what he had done before we started working together on this, he could measure the amplitude of oscillations of the membrane. You can do that. But somehow visualizing it really brings it home and lets you see the form of it. And they use that for their talks when they describe it, even though we're not adding new data. We're just adding a visualization of this. Let me just, sorry, go back to there. Oh yeah, and then one last thing. Okay, here's a cup. It's not a wine glass, so it's not quite got the resonance that a wine glass would have, but you can hear it ping, so you know it's oscillating, but have you ever seen it oscillate? No. Why not? There's two reasons why you haven't seen it oscillate. Anyone want to say what they are? Or what one of them is? So one reason you haven't seen a wine glass oscillate is because the oscillation is too small. So we'll take care of that with motion magnification. A second reason you haven't seen it oscillate is the frequency is too high. It's like 500 hertz or something, and we can't see that. And so what we're going to do is we use a special camera here that just grabs 1 millisecond of exposure each frame. And so we're going to alias down or beat down this high frequency of oscillation down to a frequency band that we can see visually. And that gives us a live demo that I'm showing you a video of that lets you visualize a wine glass oscillating. And then this beep that you heard, we have set up a speaker next to it and play it at the glass. And then it allows you then to watch the thing oscillate in real time. So now you can see a wine glass oscillating in response to a sound. And again, the special camera took care of putting it into a band that we could see visually, and then the motion magnification took care of it, amplifying it so you could see it also. So I really think that this is going to be useful for internal diagnostic medical imaging. The canonical picture of a doctor is someone with a stethoscope around their neck. What's a stethoscope? Well, it takes audio and amplifies it. That's motion magnification, but at the audio bands. Surely it's going to be useful, I think, without any basis. Surely it might be useful to amplify motions in diagnostic video imaging as well. And maybe there'll be diagnostic value to amplifying small motions inside the body. So we're exploring that in collaboration with Brian and his team. And I think there's a lot to be done there. So that's the story. This is a tool. I think it has a lot of uses. I'd love to hear your applications. And that's it. Thanks very much.
So I'll let you pick the which question you'd like to
got
take
it. Sorry.
there.
What are the stability? I'll just go. There's two tied for one. What are the stability requirements from the source video? Yes, can it be implemented? So yes, it can be implemented with microscope images and videos. Thank you. Augmentation biased or selective? You have to, so there's two restrictions I didn't quite have time to go into. One is every one of these things was on a tripod because you want to separate out the camera motion from the motion of the thing you're amplifying the motions of, the subject motion. So it's easiest if you just have the camera frozen and then you amplify the signal. So that happens kind of naturally with a microscope application. It happens naturally with telescope applications, but with handheld cameras, you have to put it on a tripod. And then for all these cases also, we're actively selected what frequencies to amplify, and that matters. It could be of interest to explore an automatic selection, but we haven't done that yet. And then the second one, could motion magnification be coupled with FEA, structural model deflection, to predict failure points? Finite element analysis, right. So, okay, yes is the answer. Sorry, I'm just thinking through. Right now this is all pixel-based, but yes, you could presumably do it in a finite element representation as well. And I think that might be value. Again, we're not giving you measurements that you didn't have, but we're letting you see them in a kind of intuitive and understandable way. For the acoustic media, can the motion amplification be done if the video is acquired with a sparse array of receivers? So there was no acoustic image that I showed. We had one where we recorded things with a single microphone, but it was a 2D high-speed video of the throat. Yes, you can, well, it might be, for this question, you might be challenged to make an image from a sparse array of receivers. So in many sense, I think it requires really an image coming in, so maybe the answer is no on that one.
Bill, thank you very much.
Okay, thanks.
Okay, Julie, come on up, and we'll impact the physical with the algorithms as well.
Well, great to be here. So initially I saw this symposium is on modeling at atomic scale. So actually we do have some work on fitting the entire periodic table. We're able to do simulations with quantum simulation accuracy, but much faster. But then I found out this is really about optical imaging, computer vision. So we do actually have quite a bit of generative AI from mining the literature data to come up with newer molecular designs for example, batteries. And here you see mixing several fluids together, electrolytes for batteries. There's still a human that's sort of operating on these kind of workflows. And recently with Tonio Bulinasisi, we have been discussing what kind of pitfalls we have in this kind of autonomous experiments. And it turns out that a lot of irreproducibility issues. You would think that with robots they wouldn't make mistakes, but it turns out that there's still a lot of cognitive issues even when you use robots. And sometimes you also can find that by changing the hypothesis, even so-called failed experiment, for example, the discovery of penicillin is really come out of a failed bacterial growth experiment. So by just changing the hypothesis, because there is really no wrong experiment, it's really wrong mind model. So if you change the mind model, then you can turn a failed experiment to a successful experiment. So in my lab, we've been looking at this multi-metallic nanocatalyst. So here we're mixing a few salt precursors, and then we drop them on carbon paper, and then later, is fast forward, we heat it up, and then we cut into electrodes. We do this test in 3 electrode experiments. And we're using active learning to change the recipe on the fly, and we do hundreds of experiments in a campaign to sort of do optimization in a multi-component alloy space. And it's kind of surprising that it took actually more than a year for us to get consistent results, meaning that if we do these different recipes on the bottom, nominally same amounts in between, we can get roughly similar results. So what are the kind of problem we had? For example, here I'm just showing this liquid drop a pipette experiment, and you would notice that the droplet size is not actually the same. So the speed at which it gets wetted into carbon strip is different. And initially we thought, okay, that's maybe because of the supplier did not give us a uniform material. That's actually one possible reason, but later we found that, just like Bill mentioned, very small perturbations. Actually, because we shock the carbon strip, sometimes they're not fully flat. And so we have this curvature, so at some point we have this bigger droplet. Sometimes it doesn't even drop at all. So it's only through kind of a computer vision that we can actually find that. And then we got this kind of garbage data because many different problems. One is, for example, after a while, the copper holder gets corroded, and the solution is we bought a few $100s of gold, and that solved that problem. So we actually identified a lot of different problems. The most sort of embarrassing problem is this one, because this hit sort of right beneath our eyes, so I can really appreciate what Bill, and it's sort of right, we see it, but we didn't catch it. So what happened was we're trying to mix multiple liquids, and this is what should happen. We're mixing two fluids, two different kind of salts, and we're doing this aspiration up and down in a bit, and that homogenized the fluid. That's what should happen. But what actually happened for more than a year, half a year, is we use a smaller pipette, and we thought it's homogenized, but because this plate is actually beneath us, so we're looking at from top down, and it's sort of just hiding in plain sight, and really give us a lot of garbage data because what we think we made was not what we actually made and drop onto the carbon paper. So we call these serial killers in the AI city. So we have cable monsters. So if you buy the cheap cables from Amazon, they somehow don't work. We have these temperature inhomogeneities. We have this coffee ring monster. This, we have a magnetic stirrer in this beaker, and sometimes it just drops for whatever reason. So we actually made this kind of things just to sort of as examples of future AI may be able to sort of diagnose these issues. But what we come to realize that we probably can use AI itself to diagnose these problems. It's very important that experiment is very different from a program, because in programs you can always reproduce the same error. But what we found is very often, for example, even if an experimentalist did everything correct, but his lab mate did something wrong in the glove box that messed his whole experiment up. And I have a situation where I had a postdoc who had a beaker which looked like this versus a beaker like this for a battery cathode, give different results. Also, I had a Korean postdoc who is leaving, and I had two students just follow him from day to the evening, just follow a synthesis experiment, and they took good notes and they did everything. But when the postdoc returned, they just couldn't repeat the result. So all kinds of issues. So what we think we can do is really to use large multimodal models and language to assist the debugging of experimental processes. So here would have sound. This is my PhD student, Zhichu Ren. He's now doing a startup company. So
I was using the laser cutting
maybe
machine to cut
larger
the plywood for making a sample stage. I set the laser cutting parameters consistent across the sample stage, but apparently I got a failure piece. Could you analyze this phenomena? Hey Meta, take a picture.
The image analysis reveals two main anomalies: non-uniform cut depths and some charring. These could be due to inconsistent material density or variations in the plywood's thickness, resulting in uneven cuts despite uniform settings. Another possibility is that the laser's focal point or distance may have shifted during the cutting process, causing inconsistency in cutting depths and potential charring.
So what's interesting is this is zero-shot learning, meaning all Zhichu did was to ask that question and then send an image. And it seems that the ChatGPT is able to give reasonable hypotheses on why that happens. So what we try to do is to prevent cross-contamination between two different droplets. So we made actually this holder to isolate the drop, but then during the laser, we eventually had a stainless steel, this holder, but when we use wood to do the initial prototype, it kind of caught fire. But then, what happened is the AI wasn't trained specifically on laser cutting wood, but apparently it has seen maybe something about lasers and something about carpentry, and is able to come up with reasonable actual hypotheses on what happened. So now we're having this log agents where the the student just have this camcorder, and it's just capturing all the things, and you don't need to even write logs anymore. So we are using it to just capture what happens in the lab. And this enables searching, but more importantly, allows us to ask questions on what might happen, what might cause some kind of irreproducibility in the system. And another very interesting thing is now we have a script-driven SEM. So this is fully automatic. You just use software to move the microscope around. But then we now ask GPT to, maybe for the first time, to control this SEM and identify martensite versus austenite. So this is a piece of steel sample that's just lying somewhere in the lab. And we have this crest system.
Crest. Please take a picture of the boundary between the austenite and martensite with field width of 80 microns.
Yeah, initially you see it's a merchandise, not martensite, but later you recognize it's a material science problem, so change it to martensite. So no human control at all. We just give it a go, and then it's sort of auto GPT. But in the physical world, it uses a script to move the SEM image center and then zoom. And then there's another thing, which is segment anything. So only 3 operations. And I should say that this is a successful example. The success rate initially is pretty low. It's like 20%. It's like a kid that's sort of stumbling around. But eventually, in this particular case, it's able to use these 3 functions and eventually identify a region of martensite that's, yeah, you're going to hear. So it has found it. Yeah.
The imaging session has been completed, and we have successfully captured a picture of the boundary between austenite and martensite with a field width of 80 microns. The process involved adjusting the initial field width, locating a region of interest, and fine-tuning the settings to achieve the desired image. The final image accurately represents the boundary as requested.
Well, it sounds pretty confident, but actually, initially, the accuracy is pretty low. But recently, we've done something which we form a committee of this AI. So we allow Gemini and Cloud and have them like 2 rounds of debates. And it's kind of interesting that these agents, for example, GPT is very assertive, whereas Gemini seems to be very, very submissive. Whatever GPT says, it says yes, yes. But then we sort of modulate their discussion. We say we have to respect each other. And then through good modulation, actually, after 2 rounds, they actually improve their accuracy through this committee approach. And we're able to use this to search for catalysts in the direct formate fuel cells. So usually humans are pretty hesitant to go above 4 or 5 elements because people generally lose intuition when the varying parameters are more than 3, actually. But with active learning and AI, we're able to find the catalyst that beats the previously human-discovered best catalyst in this 8-dimensional catalyst space. And this actually got a Best Student Paper Award in the so-called real ML, real workshop on active learning, active experiment design, and active learning in the real world award. So my sort of last slide is on in addition to this kind of physical world hypothesis and cognitive issues, we also tested that GPT have a reasonable understanding of science, and is actually able to make more abstract hypotheses. So it's actually kind of mysterious how human inspiration, right? Human scientists, right? Some people are taking a hot bath and then suddenly, come up with, some, eureka moment, right? So we think that GPT have read many more books than any individual human have done. And one very basic sort of hypothesis, we think the meaning of words are different in different fields. And so maybe in this kind of meaning space, it can do random perturbations And somehow that can lead to kind of mutations of meaning of sentences. That may be one way you can think about it, just like radiation either give you cancer or give you mutation which drive evolution. But that's, of course, a very low efficiency way to get creativity. There might be some other things if you connect with higher levels of logic, symbolic regression, and so forth. So generally, we think what needs to happen is this kind of loop where you can have hypothesis making by AI, but then also the key is what's the simplest, what's the most cost-effective experiment that can give you effective information. And then also, if I have something in my lab, but is it really reproducible, let's say, in Vladimir's lab? So I need to have some way to send the liquid or powder samples to Vladimir, even in MIT, right? So, and then also, actually, if you do this collaboration between institutions, you need ways to do material transfer agreement, which is actually a very big hassle. It's a very big friction in collaboration. So maybe some way to also sort of have IP agreements sort of packaged in addition to standardized ways of sending samples. So I think in the future, by just sort of doing this kind of iterative loop, we may have really high throughput in new materials discovery for energy and other fields. So with that, I'd like to thank you for your attention. If you're interested in this, feel free to contact Zhichu, who did all this work.
Hey, so I don't see if there's a pigeonhole question up, but please. So just a probing question from the audience. But so where do you see the sort of the problems with sort of connecting to the physical experimentation? Like, physical hardware has control systems and sort of user interfaces. What is that? What's the connective piece to like how you actually get the machine to then move the robotic system to do what you want?
So in our experience, it's like a really multispectral and a multi-dimensional sensor is really the key. Is if we do have cameras, at a low level at different angles, and not just like in the visible spectrum, and if we do have acoustic sensors, I do think those information, including Bill's small motion, those do have lots of information in there. And then we need to have this logic engine to analyze all this sensor data. I really think that with AGI, you really can get a lot more from your sensors and vision.
Okay, very good. See, we have no pigeonholes. Okay, so I think with that, thank our colleagues here, and that concludes that session. So thank you.